Hello, welcome to the sixth video on vectors. In this video I'm going to discuss a few applications of the vector product, and actually we'll look at even more applications of the vector product in the eighth video on additional applications using vectors. But in this video we'll look at just two applications. So the first one is determining whether three vectors are coplanar. So by coplanar, we mean that the vectors are all tangent to the same plane. You can think if you put all three vectors with base at the origin, then the heads would all lie in a single plane. And so sometimes this is something we want to determine. How can we determine whether three vectors, A, B, and C, if we're just given three vectors in 3 dimensions, are all in the same plane, are coplanar? Well, the three vectors A, B, and C are coplanar if and only if A cross B dot C, that's the scalar triple product, which I introduced in the last video, is equal to 0. And the reason for this is that the three vectors are coplanar if and only if the parallelepiped that they describe, that they span, is really just contained in one plane. And so the volume in that case of the parallelepiped would be 0. And so here's the reason explaining this. So the volume of the parallelepiped given by A, B, and C is 0. Or you can also think geometrically that A cross B would be perpendicular to the plane containing A and B. And so if you take the dot product then with C, that's 0 exactly when C is in the same plane as A and B. They're all coplanar. So both of these explain why this is a condition for three vectors to be coplanar. So let's look at this example. We have these three vectors, A, B, and C, and we want to say, are they coplanar? Do they all lie in the same plane? So not so obvious just from looking at them, but we can use this condition in order to fairly easily determine whether or not these three vectors are coplanar. So we just need to first calculate the cross product of A with B, and then take the dot product with C. So let's first calculate the cross product of A with B. We'll use the same method. We'll do this using the same method that I introduced in the last video with the determinant of a matrix. So we write this matrix with I, J, and K along the top row, and then the entries of A in the second row, which are 1, 1, and -1, as you can see in the slide there. And then the entries of B are 0, 1, and 1. Okay, so we compute the cross product by computing this determinant. We go along the top row, so we have I times the determinant of this 2 by 2 submatrix, which is the diagonal entries multiplied together, 1 minus the off-diagonal entries multiplied together, so that's 1 minus -1, going to be 2. And then we have minus J times 1 plus K also times 1. And so this cross product is 2I minus J plus K. All right, and let's check whether or not that is whether or not that vector is perpendicular to the vector C. We know this is perpendicular to A and B. If it's also perpendicular to C, then C is coplanar with A and B. So we take the dot product of C with this vector. And the first entry of C is 1, so we have 2 times 1. Second entry of C, the J entry, is 2, so -2. And the third entry of C is 0, so 1 times 0 is 0. And you can see that this dot product is 0. Therefore, the three vectors A, B, and C are coplanar. A, B, and C are coplanar. They all lie in the same plane. They're all tangent to the same plane. Okay, so this is one application of the cross product. Look at another application determining the equation for a plane. And so remember in the previous video we discussed how to write down the equation for a plane when we knew a point in the plane and also a normal vector to the plane. Now we're going to discuss how to write down an equation for a plane if we're given 3 points that are in the plane, and those 3 points are not on a straight line. Of course, if they're on a straight line, they don't uniquely determine a plane. So how can we do this? We can use the cross product in order to create a vector which is orthogonal to the plane. This is the idea. So we find 2 vectors that are tangent to the plane, and then take the cross product of those vectors in order to find a vector which is normal to the plane. And so I'll illustrate this with an example. So we have 3 points, A, B, and C. And I'm just drawing the points arbitrarily, not trying to put them on any coordinate axes, but we have these 3 points, A, B, and C, which are all in a plane. And we want to find 2 vectors that are tangent to the plane. So one such vector will be the vector from A to B. Write that as AB with the arrow. And another such vector will be the vector from A to C. Right, this is AC with the arrow over the vector. And so these 2 vectors, the vector from A to B and the vector from A to C, will both be tangent to the plane. We can take their cross product in order to find the normal vector. So normal vector n will be orthogonal to both of these 2 vectors, therefore orthogonal to the plane, and then we'll have the normal vector for the plane. This is the idea. So first, let's calculate the 2 vectors, the vector from A to B and the vector from A to C. And the vector from A to B is going to be equal to the position vector of B, it's the vector from the origin to the point B, minus the position vector of A. So the position vector of B is just the coordinates for B. So 2, 1, 0. The position vector for A is the coordinates of A, the point A, 1, 1, 1. So if we subtract these, we have the vector from A to B given by 1, 0, negative 1. All right, now we need to determine the vector from A to C. Okay, so the vector from A to C is going to be the position vector of C minus the position vector of A. And the position vector of C, the coordinates of C are 1, 2, negative 1. And we subtract the position vector of A, which is again 1, 1, 1. And we get 0, 1, negative 2. Okay, so we have these 2 vectors, the vector from A to B and the vector from A to C, and we take the cross product of the 2 in order to find the normal vector. So find this normal vector, and by taking the cross product of these 2 that we've just determined. Cross product of the vector from A to B with the vector from A to C. Trying to get it all on one slide here. Okay, so there we go. This is the vector from A to B, this is the vector from A to C. So let me form the matrix we need for the determinant here. We're taking the determinant of this matrix. In the second row, we put the vector from A to B, so that's here is 1, 0, negative 1. And the third row, we put the vector from A to C, 0, 1, negative 2. So this will be a kind of easy one to calculate because of the 2 zeros. So we have everything there. We don't need the previous calculations anymore. So we expand the determinant by going across the top row. We have I times determinant of this submatrix, which would be 1. So it's just I. And we have J times 2, so plus 2j. So remember, it's negative j, but then we have the negative 2 here, which the negative signs cancel out. And then k times 1, the determinant of this 2 by 2 submatrix. And so this is the formula for the normal vector. I've written everything else in this case in terms of column vectors, so maybe we should write it as a column vector 1, 2, 1. All right, so here's the normal vector, and now we have to remember back to the previous video about how we wrote down the equation for a plane. When we know the normal vector and a point in the plane. So recall the equation for a plane is the normal vector dot with the position vector of a point in the plane labeled r minus the position vector of a known point in the plane a. And so here this would be the position vector of the point a equals 0. And this is saying that the vector from a to another point in the plane r is got to be orthogonal to the normal vector. So if we move the n dot with the position vector of a to the other side, we have that this is n dot r equals the normal vector dot product with the position vector of a. Right, and we've calculated already what n is, so n was 1, 2, 1, and the position vector of a was 1, 1, 1. And so the right-hand side of this equation is 4. And so once we've put all of that in, we get that the equation for the plane is n. So I should write in what n is. So n is 1, 2, 1. Dot with r equals 4. Okay, and if we, as before, write the components of the point that's represented by r as x, y, and z. So if r equals x, y, z, then this equation, it becomes x plus 2y plus z equals 4. Right, so these two equations are saying the same thing, giving the equation satisfied by all points on this plane. Okay, so this is how we can find the equation for all the points on a plane when we know just 3 points in the plane. We first find 2 vectors tangent to the plane, take the cross product to find the normal vector. Okay, so that's the end of this video, to have these 2 applications, determining when 3 vectors are coplanar, and then also finding the equation from a plane for a plane from 3 points on the plane. In the next video, we're going to discuss another kind of way of multiplying vectors together, which involves 3 vectors, the vector triple product. We already discussed the scalar triple product, where we get a scalar from 3 vectors. This is another product where we get a vector from 3 vectors.